Buenas tardes. It is my pleasure to introduce you today to Lauren Hallett. She's here on sabbatical. She's an associate professor at the University of Oregon. Today you will see the awesome research that Lauren does, both theoretically. She works a lot with, for instance, mechanisms of maintenance of species coexistence based on fluctuation of the environment, but also she does an amazing job in restoration as well as improvement of ecosystem management. So I hope you enjoy as much as I do that Lauren is here, and the floor is yours, Lauren.
Thank you so much, Oscar. Is the microphone working? People can hear okay? Okay. All right, well, it's really a pleasure to be here, and I've enjoyed working with Oscar for about 5 years now, and it was time to visit. And I've met a number of you to meet. Please reach out if any of this wants to spark a conversation for you. So I'm going to be speaking about how to come up with approaches for conservation in a changing world. And I'm going to focus on two of my favorite ecosystems that need creative conservation solutions. So I'll be talking about two systems on the west coast of the US, serpentine grasslands and oak-prairie savannas. But before I start talking about them, I think it's always helpful to take a step back when you start a research project or start a new initiative and think about how you got to the questions that you're asking. Like our science is only as good as the questions we ask. And so that process of how we get to those questions can be really important for shaping both what you do in the field and its impact. And so I would say that the type of work we do spans a gradient from what I would call very basic science. So this is kind of pulling on theories of biological diversity, going to the literature, kind of thinking very much why are species coexisting, towards more applied questions like, okay, here's this problem, can I apply my ecological theory to solve it? To what I call very translational approaches, where you don't come in with a priori goals per se, you come in by building relationships and then through those relationships identifying what the questions are. And so I chose these two examples because I think the first is a kind of way that I've been thinking about using basic science to improve conservation, but the second is very much one where we take a translational approach. And so this talk will be divided into two segments, the first theoretical and second translational. Uh-oh. Okay, so the first one is going to be thinking about how we can use long-term basic science to understand the drivers of change in an ecosystem and then identify solutions. And for this, I'm going to be talking about serpentine grasslands. And to orient you, because I'm coming from the US, so here's the west coast of the US. And my site is located, this is very, you know what, we might just do this. My site is located in the San Francisco Bay Area, so kind of zoning in on California. It's actually Stanford's research station and biological reserve. And this is what it looked like in 1983. It was a good flower year in the serpentine. So this area here is the serpentine system that I work in. It's pretty obvious and it's pretty darn beautiful. And the reason why you have those beautiful, colorful flowers is because the soil structures the divide. So in the areas we're on, there's a fault line. So there's a lot of earthquakes, volcanic activity that brings up serpentinite rock from, and it becomes a major part of this system. And so that rock, it's really high in heavy metals. It's really low in nutrients. It doesn't hold water well. It's basically just a really shitty place to live. And if you're gonna live there, you have to be able to hack it. So you're gonna be really small because there's no resources for you to get bigger. You're gonna have a lot of tolerances. And because of that, because you're so specialized on this serpentine soil, it means it is a major conservation hotspot for California. So 1% of the California land area is serpentine soils, but 10% of the species that are endemic to California are serpentine specialists because it's created such a unique environment. So I started working in this system with my master's advisor and now long-term collaborator, Richard Hobbs, who had started in the 80s at this particular site, this particular serpentine grassland, and he was asking a lot of questions about spatial variability and coexistence. He put some plots in to study it, but we quickly found out that while there is a lot of spatial variability, there is a ton of temporal variability. So just as an indication, he put these long-term plots in, and he measured them every year. What we found is over time, every year you go, it seems like a surprise. And so we had that really beautiful California goldfields years that we saw in the aerial photo and we see at the beginning. But sometimes it's much less showy, but still really important flowers. Other times it's more grasses. And to put some data on this, I'm going to focus on 3 species that I think are really important either as indicators or just kind of in their own right for conservation. So the first is a species called Plantago erecta, and it is the dominant native forb in the serpentine at this site. It is also the host for the Bay Area checker spot butterfly, which a lot of population theory was developed by Paul Ehrlich on this species, and it is now a very endangered species. And so Plantago is really important for both kind of the history of ecology at this point, but also for this conservation legacy. And what you can see is it has these very cyclical populations where and it is the case that these cycles, the troughs are getting just a little bit lower over time, right? The second species that I'm going to focus on is Leia platagosa, and it's important. It's while the Plantago is for a larval host for the Bay Area checker spot butterfly, Leia is a nectar resource, and so these two are both kind of, the combination's really important as host species. And it had this really interesting trajectory where, oh no, I should have piloted this. I give up. It has this very interesting trajectory where it was very low abundances for most of the time series. And then there was a period of time where it gradually increased, and then it crashed. Just kind of hold that in your head. You can see that's on that bottom right corner, what it looked like. Oh, you're gonna, okay. Just give up. And then finally, the third species I'd like to call our attention to is Bromus hortiaceus. You may know it. It's common here. It's a really invasive grass in the serpentine. And so what we can see is early in the time series, Bromus came in. It was an El Nino year. It came in for a while, then it totally receded. Wasn't in the system much at all. This is a system that's mostly native. Most of California grasslands and completely invaded by annual grasses like Bromus. But because the serpentine is so hard to live in, there are these conservation refugias at this point where the annual grasses haven't come in. So it's kind of surprising when it came in for a little bit in the 80s, but then it dropped out. And then it started to come back in, and it's pretty high peak in the mid-2000s, dropped out again, and now it's come back up. And at this point, there's a lot of grass in the system. So I would kind of characterize this as sort of a cyclical invasion pattern, but also one that's ratcheting, where those peaks are getting higher over time. Okay. And so when we're thinking about this system, we've been doing a lot of basic science and a lot of just long-term observations as we're surprised from one year to the next, keeping these time series going. And we're at 42 years now, which is not, thanks to Richard. But we're also seeing these patterns of change. And so question is, can we think about what these drivers of change are? And the first one that's really been an issue for a lot of these systems in California is atmospheric nitrogen deposition. And so, the Bay Area is very urban. There's a lot of people driving. There's a lot of industry, and that's releasing nitrogen into the atmosphere that can be dry deposition on the plant. So it basically provides a direct nutrient to the plants. And we've seen time and time again that if you add high nitrogen deposition, this can create a conversion from native forbs to non-native annual grasses because you provide a nutrient release in the serpentine and other grasses. And the second driver is we have highly variable rainfall. And I think you guys can empathize with this at the moment. But just to kind of call your attention to it, the first year of the time series when Richard was working in this site, we had 1,200 millimeters of rain. And a couple years later, we had closer to 200, 300, right? So it's a huge variability in the amount of rainfall that these systems get. And so if we're thinking about these two drivers that are also often the two primary limiting resources in California grasslands, also in serpentine grasslands, we can start to draw an ecological theory to why it is that you maybe have these oscillating populations over time and why you might have these invasion patterns, but also these ratcheting cyclical invasions. And the first, this is me, the work of one of my master students, Elisa Hernandez, but her first hypothesis was that perhaps when the ability is when you have an intermediate level of nitrogen deposition. And her reasoning was as follows, and she was drawing from R star theory, and she said, okay, if you're in a really low nutrient environment, the species that is going to be the most competitive is going to be the one with the lowest R star for that environment. So, for example, if you're in a historic serpentine grassland and there's very little nitrogen, the species with the lowest R star for nitrogen is going to be the dominant one. So you can see that on the far left-hand side, where the conservative species, maybe that native plantago, would be the one that dominates. But if you start to add resources and you relax that limiting resource, as you might see with nitrogen deposition, so that'd be the black line, at some point you're going to shift where it's entirely the nitrogen doesn't matter anymore. Your acquisitive species is going to do well. But you're going to have a spot where the amount of nitrogen deposition you experience essentially equalizes the fitness between these two species, so that they're becoming, at that point in time, fairly neutral to one another for that resource. And that's when we hypothesize they might be more likely to be influenced by variability in other resources. And you could also think of this as in a resilience framework, where you could say at low nitrogen deposition, you're going to always converge to a native conservative state. And so you might start with a system, you could start with a system even that has a bunch of annual grasses, but you add some of that conservative species, it's going to do well, it's going to eventually dominate. So even if you start in an exotic system, if you're really low nitrogen, you're going to get pushed back. Similarly, in a high nitrogen state, you could start with a community that has a lot of that native plantago. You could start with a community that has a lot of bromus, but if you're at a level of a sufficient nitrogen, that bromus is going to increase and it's going to completely wipe out the system. But at intermediate levels, you might see some toggling. A dry year, it might be the case that it will converge to plantago no matter what the starting conditions are. But if you have a wet year, it might be enough to add enough resources for those acquisitive species like the bromus that you toggle to being more of annual grass dominated. So that would be one way that we could think about that increasing invasion, but also that it's cyclical, because as you start to hit a certain level of nitrogen deposition, you're going to vary with rainfall before you eventually become completely converted as a state. Elisa's second hypothesis was that global change and probable availability will generate nonlinear invasion dynamics. And so you can think about this, this is adapted from a framework by Mendy Smith, but you can imagine that at first, when you have a system that's experiencing change, the first signal of that will be the species that are already there are going to reorder in their rank abundances, right? So before you have a chance to have new players enter the system, you just see a reordering. And that could be what we were seeing with that signal of the lay starting to increase. This is a bit more of an acquisitive native species. Maybe that was our signature that there was some directional change. And then ultimately you have species that immigrate that are better suited to the new conditions. So this would look something like this. At some point in time with some level of nitrogen deposition, maybe you see a reordering between the two native species and those toggle. But eventually, we get enough non-native seeds into the system that are better adapted to those new conditions, and then you start that toggling between a non-native state and that original, more conservative native state. So these were Elisa's two hypotheses. And to test them, she created different water by nitrogen conditions in the greenhouse. And so she had a low nitrogen version where we had serpentine soils from an area that didn't have nitrogen deposition. And then she added to create an intermediate nitrogen and a high level of nitrogen deposition based on records in the Bay Area. Then she also had a dry environment and a wet environment. And within these, she did an experiment where she have each of my 3 focal species, that conservative dominant species Plantago, the more recent acquisitive subordinate native species Leia, and that invasive annual grass Bromus. They'll either be alone or they're going to be alone with a background of each of the other species at increasing densities. And so by doing that, you can see what it looked like in the picture on the right. You're able to isolate the effect of the environment versus the neighborhood community on each of the species' performances. So she did this and she measured seed production based and compared it to what was added. So with this, she fit population models. She said, okay, for example, the number of Plantago seeds at time t+1 is a function of its intrinsic growth rate, lambda, as well as the number of seeds you added. So per individual seed production, number that were added. And it's going to be moderated by the amount of competition it experiences from itself and from Bromus or Leia. So she did this within each environmental condition for each of the species. And then we assessed coexistence within each environment. And the way that we did that was we said, okay, let's imagine a scenario where maybe there's 2 species that are present, but you drop one out and allow the other one to reach equilibrium. So in this case, we're just focusing on the green species, allowing it to reach equilibrium. And then we invade the other species at a low density. And if it can increase when its competitor is at equilibrium abundance, it would suggest it could coexist. It's able to come back when it's rare. And if it can't coexist, or if it can't increase, it would be competitively excluded. And so she calculated this, she repeated it for each species, in each species pair, under each environmental condition, to get a signature of under each unique condition of water and nitrogen, which species could coexist or not. So this would be growth rate when rare for the coexistence folks. And so for her first hypothesis that serpentine grasslands are most sensitive to rainfall variability at intermediate nitrogen, to kind of orient you here, on the x-axis we have nitrogen treatment, so low, intermediate, or high. Dry is that light-colored gray, and well-watered is the darker gray. And we see this is for Plantago when it's invading Bromus. Under low nitrogen, it could always invade Bromus. So it was always going to be able to coexist under low nitrogen, although its growth rate when rare was lower with water. Under high nitrogen conditions, it could never invade Bromus. And so it was around 0 under dry, under wet. And then under intermediate conditions, you saw it swapped. Where under dry conditions at intermediate nitrogen, it could invade Bromus, but under wet conditions, it couldn't, which really supports her idea that when you see that switching between states for Plantago, that switching from being able to coexist or not really depended on rainfall most strongly under those intermediate nitrogen conditions. She saw sort of the inverse for Bromus. Although Bromus, it turns out, was pretty darn competitive as soon as it got nitrogen. So here we saw that Bromus could come into the system at intermediate or high nitrogen, and then at low nitrogen levels, if it was dry, it was really knocked back from the system. And if there was a little bit of water, it was in, but a pretty low growth rate. So this gives some support for her first hypothesis. For her second hypothesis, that global change in propagal availability will generate these nonlinear invasion dynamics. What she saw was that Plantago could always invade Leia. And so it's maybe not surprising that Leia kind of had at a lower growth rate over time, and Plantago is the dominant, right? It's for this system, it's generally very competitive. But what we saw was exactly what we would have hypothesized for Leia, where under low nitrogen, it was never able to invade Plantago. So this would account for why it was always at such a low abundance early in the time series when there wasn't a lot of nitrogen deposition yet in the system. Under intermediate, once it got some water, it was able to invade, but it couldn't under dry. And as soon as you hit a high level of nitrogen deposition, it was always in. And so this might kind of, if you think about a system where there's increasing nitrogen deposition over time, that gradual increase in Leia might suggest that that's the signature of nitrogen. But finally, Leia trying to invade into Bromus was never a deal, right? Like Bromus was just a more fit species compared to Leia, which might then explain the crash we saw in Leia abundance, because once Bromus got in the system, it could just outcompete it. So kind of to put this into context and some lessons we can take away from using these long-term data sets and then applying some of our basic theories of ecology towards, a first lesson is that we should treat species reshuffling and reorders and rank abundance as an early warning sign. And so that period of time when laia was starting to increase, when it had never been in the system, would probably be a good time to start some invasive species monitoring, because it's suggesting that there's some other driver that's going on in the system of that system. A second lesson would be to work with environmental variability to manage the system if you still can. So for example, when we're at that intermediate levels of nitrogen and bromus is starting to increase with wet years, maybe that's not the year to go all out with your spraying and trying to control its population. Maybe you say, okay, it's coming up, but it's toggling. Let's wait till a dry year when it's effectively being knocked back by the system, and then let's go and just get rid of any other potential propagule that's surviving in that system. Let's work with that variability to knock it back when we're in that early period where it's coming in and out of the system. So maybe we intervene really aggressively when it's low abundance and work with that variability to completely eradicate it. That's before you get a full state conversion. And then the third lesson is that the ultimate results of management may take time to observe. And in this system, there's been a lot of thoughts about how to manage it. My colleague Stu Weiss has really laid the groundwork for this, where his argument was, okay, if we're in a system where it's completely converted, where we have a high level of nitrogen deposition and it's mostly annual grasses, what we need to do is bring in something that's going to remove those annual grasses. And really showing that if we use grazing or mowing, that's a very effective treatment to be kind of restoring that balance, as sort of a top-down pressure on the species that are otherwise really favored by this new environment. And just to give an example, this is a site that Stu worked at. It was a serpentine site that didn't have cattle. It experienced a lot of nitrogen deposition. And on the left-hand panel, you can see that it basically became all non-native grasses and thatch. They brought in the cattle, and within 6 years, it had switched, and you can see that light gray flower. That's all that plantago. However, we did some analyses of kind of looking at these long-term trajectories, and what we saw was that in areas that were continuously grazed, we had those peaks and troughs of plantago. And in the area where we reintroduced the cattle from when it was previously low, we didn't see a big bounce in plantago for a number of years. But if we look at our comparisons, that's probably because it just wasn't a very good series of years for plantago in general. It has those peaks and troughs naturally. But once it was a good year for plantago elsewhere, we saw that the restoration treatment was in fact successful. Right? And so when we're thinking about a system with a lot of variability, keeping that in mind of when do you expect to see big pulses, to make sure that your expectations are kind of in line with when it would be a good time for the species at all. Okay. Okay, so that I think is kind of the chapter on a kind of a commitment to basic science and using these kind of long-term records and integrating theory and experiments and modeling to understand the system and then develop more applied solutions. Okay, it's also so beautiful, right? Like, come on, we need to keep the flowers. So the second half of the talk, I'd like to kind of switch to some work that I've been developing. I've been working at the serpentine grasslands for a long time, since I was a bright young thing as a master's student. And then when I moved to Oregon and started as faculty at the University of Oregon, I started to think more and more about the systems there, and started to interact with people as I developed my questions there. And so this is going to be an example of sort of translational science for questions and action. And so translational ecology can be thought of as basically when you bring ecologists and stakeholders and decision makers together to develop the research jointly to address a problem. And so in practice, the way that this might work is you might have some academics and stakeholders. One or the other of them says, hey, there's this environmental problem we're dealing with. And the stakeholders could say, okay, well, maybe we could work on that problem, but over you academics, maybe there's some social constraints or policy constraints that are really functioning on curtailing the system that you're not really thinking about. This happens to me quite a bit as an academic. And so having those partnerships can be really helpful for highlighting, maybe I think that something's obvious, but it's not, because there's some other social constraint. Academics are generally pretty good at providing some funding, some experimental design, bringing some rigor to kind of testing the questions that might be there. And meanwhile, stakeholders can provide other types of resources, right? So if we're dealing with land management, maybe they provide the site, or maybe they provide some of the treatments and so forth. And I think one of the big ideals for translational ecology is that each can help the other out on the things that constrain them, right? And so if there's a land manager that's like, I really want to try this, but I can't get the funding for that extra bit that's necessary for me to be able to do it, then I can come in. But if they're like, I'm going to try this anyway, I can be like, well, can I leverage that and maybe add some experimental design to make it really more rigorous? And then finally, as you kind of go forth in this iterative process, you develop the sort of products we like as academics, but you also can develop new questions. And so as an example of how this has worked, at least in my life, we're going to focus now where I live now, which is in Oregon. So we've gone north from California in the Serpentine to the Willamette Valley, which is it's a system that has historically been oak-prairie savannas, and now is a lot of hazelnuts. So this is sort of what it would look like before. The oaks are a little dense in the back, but in that foreground, we've got our oaks, we've got our flowers, sort of understory. This is maybe the nicest. This is Mount Pisgah. It's maybe the nicest remnant we've got. We don't have a lot of nice remnants of these oak-prairie savannas. And one of the reasons we don't have a lot is that a lot has been converted to agriculture. And so this here is a hazelnut orchard. And as you can see, the intermittent oaks are gone. We've got these hazelnuts in rows, and there's nothing on the understory. And so the question was, how do we conserve and restore these oak prairie landscapes? And I want to focus on the oaks first, and kind of present a problem that was brought to me when I was a very junior assistant professor. And I showed up, I had a website that said I was a restoration ecologist, and I got an email from a hazelnut grower. And he had his family's farm, and they were trying to convert from grass seed production to hazelnuts. They'd already converted some, they were trying to convert more. They were also really being diversified. They have bison, they have pigs. And he came to me and said, listen, I've got this kind of sort of restoration-themed problem, and I'd like to talk it through. And his problem was that the primary insect pest in hazelnuts is this moth called the filbert worm. And the filbert worm will fly around in the summer and mate, and then it will bury its eggs inside the nut. And so this happens around September. Harvest is normally September, October. There's a lot of if you have a lot of infested nuts, processors won't even deal with you. You're done. The worm comes out of the nut and then overwinters in the ground, and then it hatches and it flies around in the summer again. So he had these great. I should maybe back up a sec. He had this problem, and the way you deal with this if you're organic is that you need to get all the nuts off the ground in the fall, and if you do that, you'll break the life cycle of the moth, right? Because you get every nut that maybe they're in, and it's super labor intensive. You're mowing all the time to have the ground be clear, and then you're trying to get all those nuts off. But he was doing it well. But his problem was that this moth is actually a native moth in Oregon, and its host is the Oregon white oak. And we've lost all but 5% of our oak lands, and he happened to have these gorgeous oaks right next to his hazelnut orchards. So he was really worried about pest spillover from the oaks to the hazelnuts. So this was his problem, and actually he jump-started us in the translational ecology little cycle because he also had an idea for a solution. And his idea was that if we're having these moths burrowing into acorns and increasing the moth population in the oak hazelnut stands, could we, and I put this example in because my God, the Spaniards would have thought of it a lot sooner, could we graze the infested acorns with the pigs that he already had? And the idea was that it would be this win-win-win solution, right? Like we would be breaking the life cycle of the moth in the oak stands. So we deal with his pest pressure in his hazelnut orchards. We would also keep the lovely oak stands. I would say some people told him just to cut them down. Like it was not great. And then finally, we'd have some really delicious pigs. And so we said, okay, let's try this. And this is a project that was actually largely led by undergrads and grad students. And so what we did in this translational framework, he comes to me with a problem that I never would have thought about, and also said, hey, maybe we could do this. And I said, okay. if we're going to do that, I can help you with an experimental design. I got some money to pay, a student crew to do this. He provided the land and the pigs and the implementation, so it was really this kind of collaborative effort. Here's our pigs and our oak stands, and they went nuts. And we measured both the emergence of the filbert worms, and so we have these traps here that have a pheromone ring at the top, and so we could see if they were coming out of the soil. And then we also measured their aerial abundances and basically seen the full population. And so what we found was that the grazing really effectively reduced pest pressure. So focusing on just the emergence of the left-hand panel, we did this over 3 years. And what we saw, the pink is the grazed, and the number of filbert worms we were getting in each trap from the emergence was really reduced immediately from this practice. And in terms of abundances, I would say in the first year or two, we had just our plots. And then we were like, this is great. Like, your pigs are super tasty. This doesn't seem like a lot of extra work for you, and you're getting some benefit. And we're seeing this emergence. So then we scaled it up across the farm, and we started to see then that the overall aerial abundance also really decreased in the areas with grazing. And so this to me was like, this is kind of an easy test case of translational ecology, because everybody was kind of working towards the same goal, but also a kind of nice one. But while we were doing this work, I had originally been worried about having these pigs in these oak woodlands, because I was like, the understories, I don't want to trash the understories, but if you look back at this, you can't super well tell, but most of that understory is invasive blackberries that we actually don't super care about. Like, it's a big problem, right? And Oregon historically has been a very nice place to live. It's got a really nice climate, and people like it, but a lot of invasive plants do. So we have a huge invasive plant pressure in our oak woodlands. And so it seemed like this worked pretty well for the pigs. But if we're thinking about what do we do? Okay, we're keeping some oaks from this practice, but what about this oak-prairie savanna? How do we conserve and restore the oak-prairie side of it? And when my students were out there doing this work, they started talking, and they were like, we've also been doing all these trials where we're trying to restore the oak understory, and it's like, it's not working. Like some of the solutions people had were plant only the native grasses that are so thin leaves that when you herbicide it all, they live, right? Like, which wasn't super compelling to me as a conservation solution. But we were looking over in these oak woodlands, or these hazelnut orchards, and we were like, there's not any invasive species in that understory. Like, they've actually taken care of a lot of that problem. But there's also all these problems that are coming from having bare grounds in our understories, right? And so there's a lot of erosion in these orchards. There's a lot of chemical runoff in these orchards. And the reason they keep them as bare ground is when they harvest the orchards, they harvest off the ground. And so a lot of the kind of conventional species that people suggest as cover crops have been developed to put on a lot of biomass to grow quickly, but you don't want those in the fall potentially entangling your nuts. So people spend a lot of energy kind of spraying and mowing and scraping these orchards, and we thought maybe there's a better way. And so we came at it from a conservation perspective, and we thought maybe could we find native plants that don't have some of the problems people are associating with conventional cover crops, but we could use them to kind of restore those oak prairies under these hazelnut orchards. And initially we're coming from this perspective of, can we bring some of that native plant diversity back? And so we started with some small plots, and what we found was when we used these native cover crops, the phenology of the native plants worked really well with the timing of orchard management. And so in the fall, with the fall rains is when you have the little native plants germinate. They germinate, but they don't get super big because they know that winter's coming and they need to stay small because it's going to be cold and it's going to be dark. And so in the fall, what we found for the native cover crops is on the left of each of these panels is what it looked like conventionally. On the right is what it looked like with these native cover crops. It looks effectively the same. So this is when they're harvesting and you just don't see much plant material. In the winter, what you can see on the left is that without having anything on the ground to stabilize it, you have a lot of rutting. What that means is that they then go with a scraper to get it all even. But on the right, what you can see is there's enough plant material. There's some above ground. There's a lot more below ground. And what that's doing is it's stabilizing the soil so they're not having that rutting. In the spring, historically, people would be mowing like every 2 weeks or so to keep any weeds that were on the orchard floor down. Instead, we had these diverse wildflower mixes. They looked super beautiful, and we found they were very effective at suppressing weeds that would otherwise interfere with harvest in the fall. And so they had a lot of biomass going in the spring, but they were keeping weeds that would be potential problems down. They were increasing that organic material. And then finally, by the summer, in a conventional landscape, you would be scraping the ground because you had all the ruts from the winter. But what we were finding is you could mow basically once in the spring before they sprayed for insect pests, because we didn't want to attract a bunch of pollinators to flowers. So we got rid of the flowers before any possible spraying. And then we mowed twice in the fall to kind of break it all back. And that was sufficient for getting this bare ground. So this was our life cycle. At first we were a little dubious, were they even going to survive? But what we found was that these cover crops could very well tolerate farm operations and could even thrive under them. And so here's survival in the orchards. We've done this particular site's been going for 5 years now. If we don't do anything, or we flail, or we scrape, the percent cover is the same. And actually, you don't really need to scrape once you start doing this because the ground is much more stable. And then the real kicker for us was we started to see that there was actually benefits for the farm in doing this. And this became really clear to us when we had a wet fall, where generally, if you have a wet fall, the ground gets really, really muddy, and it's hard to get the nuts off the ground. But when we had our cover crops, there was enough root material in the ground that the nuts didn't get lost in the ground. And so we saw this was basically the number of nuts that got lost or entangled on the ground. There was much fewer in the areas where we had this than in areas where we were having kind of standard practice and they got pushed into the ground. And they're also rocking it. So it's really beautiful to go out there. Well, to me, it's beautiful to go out there. Some people like this clean orchard floor. We're working on the cultural side of this, but they're rocking it. We're even trying to do camas, which is an iconic plant. It's a bulb in Oregon. It's not very effective in terms of all these farm benefits, but man, we're excited about it from just a conservation benefit. And so I kind of include this example of translational science as often grower-led, and that kind of engagement for us with growers, helping us to identify questions, but then also come up with new ideas, identify different types of constraints. You know, a lot of the practices, the seed mixes and so forth, have been developed with partner farms that are like, this could be really cool, but what about this? Or the biggest problem for us right now is native seeds are expensive. So they have lots of ideas about how could we kind of work on this. And it's really been this kind of developing partnership that I hope will mean that someday when we drive around, we just see wildflowers where we now see bare ground. And with that, I'd like to thank you so much for coming to the talk and then for hosting me for this month. And I'm open to any questions.
Thank you so much, Lauren. That was an absolutely amazing talk. I'm sure you all agree. We've got plenty. Have we got plenty of time for questions? I think so. Who wants to get us started?
Thanks, Lauren, for the very nice talk. I'm just curious, why did you mow the wildflowers, and why did they wanted pollinators in the farm, like under the...
Oh, why did we mow them when... Yeah. So the question of when to mow the wildflowers in the hazelnut orchards is a bit complicated. So almost all of the hazelnut orchards are not organic. So they're conventional. And the way that they're dealing with the filbert worm is not by having, getting all the nuts off the ground and having pigs at other places. It's just by spraying. And we didn't want to create an ecological trap where we had all these flowers and then they sprayed. And so we have a lot of criteria for how we select the species. The biggest one is that it's not going to mess up farm operations. So we had 1 or 2 that didn't break down in time in the fall, and we're like, you're out, you can't be there. But we also are very selective on species for their phenology, so that they flower early enough that they can their populations can perpetuate without additional seeding. But we're also not bringing in the pollinators. Oh, at the wrong time. They're great for the pollinators until they're not.
Since I'm done, in the other you showed the, the cattle eating and then the pig on the plantago.
Yeah.
That they both grow better, but in the last 2 years or 3, they go down again. Do you know what's happened?
I think it's climate. I think so. It's why, like plantago, it peaks, it troughs, it peaks, it troughs. I think it's a climate driver. My grad student Jasmine Albert right now is leading some analyses of synchrony and population abundances across different serpentine sites in the Bay Area, thinking if we see a lot of synchrony with them, it would be a sign that there's some environmental forcing. And what we see is that there's, in areas that have all the same topography, there is a lot of synchrony. And so I think it's not just like, it's a little bit rainfall, but I think a big part of it's also temperature, and that's kind of synchronizing them. So I think it's just an external environmental driver.
Thank you.
Hi, thank you very much for this wonderful talk. And I think you mentioned temperature, and this is also something I wanted to ask from your first part, where you showed that in the serpentine salt communities, it's the nitrogen and the rainfall which you identified as the 2 important drivers. But then also you're in a very seasonal climate, I suppose similar, Mediterranean climate. What about like extreme temperatures in the summer, for instance, because they've been shown to be quite important, and this is what's really changing now globally and stuff. Do you have an idea of how they may impact?
Yeah, that's a great question about the, and not just kind of resource drivers, but also temperature drivers in the serpentine. What I would say is that I think for the annual grasses, the resource drivers are probably the biggest drivers for them in the serpentine, because if they don't have the resources, they just can't do it. That said, as it's getting hotter and drier, that also can tip the balance towards these annual grasses. And we see that a little bit in California, but it's already so converted that it's less of a signature. We see it very much in Oregon, where it's been getting warmer in this kind of pretty lockstep since the 90s. And we've done a lot of satellite images to show that that's increasing where the annual grasses are relative to more perennials or to flowers. And so I think that temperature signatures are a pretty big deal. I think it's a little bit more for these particular species, tipping the balance more a little bit in the more northern latitudes where you're starting to have that switch.
Thank you. I would like to ask you about the last project of the translational thing, how they scale up, because we are also working with farmers here, and you always have these champions which are really involved and motivated, and that works for them, but it's really hard to scale up. So is in this area just showing evidence create an impact in the rest of the farmers?
Yeah, scaling up is super hard. So I would say the first example I gave is maybe the most ideal test case scenario of how this could work. Like, I was motivated, the farmer was motivated, we all kind of had the same goal. But oftentimes in this work, you don't have the same goals, right? And so maybe people are really coming from a conservation angle, maybe others are coming from a production. The goal is to find ways that those things are mutually beneficial, but that can often be challenging. And even when you find a way that's mutually beneficial, if there's been a legacy of viewing conservation and production at odds, there can be a lack of trust, so that it takes a while for people to say, oh, actually, this could be mutually beneficial. I would say the way that we have dealt with this is to start small, to kind of test pilot these things with willing partner farms, but then at the same time to just show up and listen. So the hazelnut industry in Oregon is actually pretty centralized. They have a nut grower society, they have summer tours, they have winter meetings, they have coveys where they all meet, and we just go. Like, we go. For many years, we just went and listened and asked questions. And then we kind of tested things with willing collaborators. We took those meetings to say, what are some of these other constraints people are facing? And we started building up. I think it very much helps that the student on this, who's now the research associate, is a 4th generation hazelnut grower. That has helped us immensely to have that as a bridge. And then we made some mistakes. We definitely made some communicating mistakes early, but I think we overcame that by showing up and building trust. And also we overcame it by bringing money. And so at this point, we have a very large grant that will cover 20 different partner farms to do this. And now, when early people were like, we're not so sure, we're not even having to advertise. We just get so many emails. So.
Thank you for your talk. I know not much about plant physiology, but it seems to be interesting that interaction in the abundance, relative abundance between bromus and plantago, I think. Mm-hmm. Because some species, I don't remember, it was better when at wet years and in nitrogen soils. I don't know if plant absorption nitrogen is favored or for these species or not.
Mineralization in the soil, and I would imagine that combined with the deposition that's happening on the plant tissues would combine to have an effect. So I have not, I would say one of the nice things about this site is that we have kept studying there for 42 years. But one of the drawbacks is neither Richard and I have lived near there for very long at all. And so some of these more detailed types of studies that you would want to do, over the course of the year to really get a signature of when are the nitrogen pulses, how much does it relate to water, we haven't done.
Any other questions? No? All right, then. I think with that, then, we'll say thank you again. Absolutely wonderful talk. It was an absolute pleasure. And
thank you all.